Is it okay? Okay. No sound? Strange. There is? It's okay. Great. So today I wanted to discuss just Mumford quotient, stability, and the Hilbert-Mumford criterion. So we start with the following problem. So suppose you have, so you want to discuss embedding of x in projective space, where x is where G a linearly reductive group. Acts on linearly on V. So then you can take projectivization and take the inclusion of X. So take some projective sobriety. And the question is how to take quotient. So how to construct quotient. And there are a few problems here. So the problem is that you cannot construct a quotient on the whole space X. And for example, there could be rather silly examples like you take the projective space with there are if V is so here we didn't discuss this particular examples, but it can happen that if V is reducible, so that it will happen that V has so P of V has a unique closed orbit, so has unique closed orbit. So this gives you, so this is actually G mod P, where P will be the group containing some Borel subgroup B. So this, and then you will have the troubles that if you want to construct a reasonable quotient, the quotient should be just all orbits. So the values of the function should be the same on all orbits, and all these orbits contain this orbits in the closure. And so at least if you are thinking about, and also it's not clear about the regular functions on X, because regular functions on X do not distinguish your variety. So there are quite a lot of problems here. But what we already know, that we can take categorical or good quotient on affine variety. Yes? So we can take good quotient, categorical quotient, when X is affine. And this was done as taking the spectrum of the ring of functions on invariants. So the idea tried to reduce, so the idea is try to construct a covering, try to construct a covering, a G invariant covering. by affine open subsets. So how to construct such embeddings? Usually, if you're thinking about embedding, then you may think that here on projective variety you have the section, the tautological bundle, so tautological line bundle of hyperplanes. Line bundle of hyperplanes. So this will give you the following. So this will this inclusion that we consider here give, or actually any map will give you as a pullback, so you can pick up the line bundle. And this, so since P of V has a natural linear action, then just G acts on, so acts on P of V linearly. So this allows you to have the action on the sections of action on the sections of on the sections of 1, and notice that the sections of 1 are just identified with V dual, so the set of coordinates here. So the, or you can think of them as the collection of homogeneous coordinates, and you may think that you are acting just so thinking of the, and there is a corresponding vector, just EXI, EI, and you are thinking about that you linearly can act on the vector, or you can act on the set of homogeneous coordinates, and this gives you actually the linear action on the section. So this also, if you have this pullback, this the action on this set of sections provides you the action on the set of, I mean, if, so in some special cases, if, for example, all the, you know that all the sections coincide with, of L coincide with P of V, so this gives you the action of G on the section, so this suggests to introduce the following notation. So L is linearized. So I'm recalling the definition. If the following diagram is commutative, so you have the action on the line bundle as just that extends naturally the action on X, so there's this is lifting of the action, this is action, this is identity times projection, so P, and this is projection. So so if first this diagram is commutative, so diagram commutes. So meaning that you just can take so you can take the element of the line bundle, yes, so that over the point P, so P of over the point X, so P of Lx is just X, and you can act by G, so by rho tilde on this section, and then you can project by P. Or you can think of this as acting, so this should be equal to Gx, yes, so the action of G on X. And this tells you that you can, also you should notice that, so this rho tilde should preserve zero section. So meaning that just you have, so if you are looking at the line bundle, so you are looking at it as the collection of lines where 0, so you know where is 0. So this is, so you have a natural 0 section. And the second is that it should act linearly. So if you think about the action of the map between L of x that maps to L of gx as the fiber, yes, so the fiber of P over x maps to the fiber of P over gx, yeah? So this should be a linear map, yes, so this is map. This is of course K that maps to K, yes, so but there are many maps of a fine line if you look at them abstractly, yes, so you can, for example, take the translation of the coordinate here. So, this map should be linear, so this is linear map. So since you know that the 0 is fixed, then you know what is linear map between these two guys. So this identification gives you the linear map between these fibers. So this is here, this is multiplication by the constant. So of course in more general setting, this here you can put vector bundles. Then here you have n-dimensional vector spaces. So since you know that there is an identification of the pre-image, natural identification with the vector space, so the map G should map the vector space into the vector space linearly. Yes? So you do not allow, for example, shifts the translation by the coordinates that do not preserve 0. Okay? Is it clear?
Yeah. Is it true that if G acts on X linearly, then the action extends to the action of projective space?
Just on X linearly or on the line bundle?
No. If M is linearizable,
yes,
then the action extends to projective space.
Yes, this is true, but you should say something about how to relate this projective space. I didn't yet, I haven't said how you can map to the projective space. Yeah? So so the claim that you want to say, I mean, is the following. So if L is linearized, so if if L is linearized, then G acts on the set of sections linearly, so acts linearly. So the set of sections is the vector space, yeah, natural. So G acts on this space linearly and locally finite. Yeah, so locally finite, meaning that the orbit of any section is finite dimensional. Yeah, so the orbit. So if you take the section, and if so it the linear span of the orbit is finite dimensional vector space. Yeah, so finite dimensional vector space. So you have the same situation that you have with the actions on X, and the proof is literally the same. You should notice that you have the corresponding tensor product, the map of tensor products of L into G from L into G times L, and this tells you that this set is finite dimension. So if you have this action and it is linear, then we can put in the words what you wanted to say. So we can have the map from X into Usually we had the map if x was affine, and if you had collection of functions. So of course you can map any point of x to the values of these regular functions, yeah, in this point. So these regular functions plays roles of the coordinates, and you have this corresponding mapping. So if you have x now, I mean, which is projective, of course, so you can think of, so you can pick up some basis in the set of sections. So I know, so suppose you know that this space is finite dimensional, and this is true for projective variety. So this, or you can take some invariant subset of sections that span sections span G invariant subspace. Then you want to try to construct the following map. So from x to, so you want to a priori construct the naive map as by the analogy of this one. So you want to take x and to construct the values of the sections in this point. However, it is, I mean, locally it is clear what is the value on the section. Yeah? So since if you take, so if you take the open neighborhood in X affine, so if you restrict the line bundle to this neighborhood, it will be just X times K, yeah, so the affine line, and this will tell you that you have the, so the sections are, so sections U times A. So sections are functions, regular functions. So on U, so just by thinking of the section as the map to a, so if you are identifying it, then you are having U maps to by the section to L of U, and then you have you can project it to A1. So this is a regular function, so you can think of regular functions. But what is the problem? So you have so these values of the sections are not just the values of the sections are not defined, just simply because for the following reason. So you have 0 here, so it is fixed. But in the same time, the section looks like this. But in each line, you do so you are thinking of this as a fine line. So you do not fix a coordinate. So thinking of this is equivalent that you are picking a unit in each line, and this is done consistently. So the coordinates in each fiber are picked up consistently. And here you do not have this kind of consistency just for general section. But notice that if you have two non-zero sections, so Si and Sj, where if, for example, Sj is not defined, so so Sj is not 0, so the quotient is well defined. Yeah? So even if you do not have the coordinates fixing 0, just if you fix 0, think of this as just the map between the fibers. You identifying the fibers by the linear map. This is just multiplication by non-zero constant. So the value of the sections, so these ones are well defined. So are well defined. So so the idea is to think of this map as the map to the homogeneous coordinates. So you are thinking, however, the sections are not defined, but they are defined as homogeneous coordinates. So you can think of the charts by where Si is not equal to 0. So you can pass to the chart just by the following. So pass to the chart Si is not equal to 0 and pass to the homogeneous coordinates Six divided by Si, Sj of x divided by Si of x. J is not equal to I. So homogeneous. So these are coordinates. And this provides you the map from X into some projective space. So just precisely of this set of, so precisely to this collection of sections. However, it is not defined everywhere. And where is it's not defined everywhere? It's not defined when you cannot just divide by, so when you cannot pick up a section such that you can pick it as the homogeneous, so some coordinate, and you cannot divide by this given section. And it is not possible when the section vanishes. So this map is not, so this map is not defined on the common zero set. So this is called base locus, and this is just intersection of zero set of all sections where S runs through H. All. So this either collection of sections, or if you think of this as the linear span, so this is called sometimes linear system. So L is, so this is, if you take not the whole space of sections but some subset, so this is called linear system. And this you can also introduce the base locus of the linear system, which should be larger than this set where the section runs through the elements of the linear system. And of course, yes, so this just since you may think as the section as the element of the sheaf of the ideal, so this is just so you may think of intersection as the corresponding sheaf of ideals of all sections. Yeah, so but it has actually schematic nature. Yeah, so this or schematic flavor. So you know. So thinking of S as so zero set of S as some ideal GS, so you can pick up the sum of all GS for S that runs along this, for example, linear system, and this gives you the corresponding sheaf of ideal of this base locus that defines this base locus. So sheaf of ideals defining. So it can happen that this so this base locus is empty, But what we have, so if you throw away this base locus of this linear system, then you have the map which is defined here. Yeah, so that, and what we can formulate your question this way. Yeah, so that if the sheaf is linearized, then these sections on the section is linear, and this plays role of the projectivization of the vector space corresponding to this linear system. Yeah? And here the action on V is linear. Okay?
And so in this case, that metric construct provides the embedding of X into projection.
Yeah, so this, no. I mean, if you're just in general without any assumption on L, yeah, so just this is just a map. Yeah?
But under the assumption that L is linearized.
If I mean, even if L is linearizable, if you take all the sections and you do not assume anything on L, a priori, it will have, you will have the map, not the embedding, just a map. I mean, for example, you can pick up just X is projective or complete, and for the line bundle, which is linearized, you can take O of X. But you do not have regular functions on X except constants, so this map would be to the projectivization of one-dimensional space, which is a point. So this can be expressed a little bit coordinate-free, if you like. So as thinking of just to X, you can associate the function on the set of sections, meaning that you can evaluate any section, but this function is defined up to proportionality because you cannot fix the value of the fiber. So this means that you are mapping to the projective space. So you may think of this as the map from X without base locus of L to the projectivization of the dual of your set of just set of sections. So V was the subset of sections, and a point X maps to the function, so linear function. So sorry, this is V dual linear function up to proportionality. Yeah, so just up to proportionality. And this is just saying that this linear function on the section is evaluates. It depends on X. Yeah, so this to the section it evaluates. So you take the value of the section, but this value of the section, again, since we cannot fix the unit here in the section, it is just the value up to proportionality, so that this is projectivization of this vector space. But in the coordinate, maybe it is for beginners when you come with, so when you get this notion, it's easier to think of this. We are just picking bases, and we are just picking, looking at the values of the section up to proportionality. Okay. So the idea is to just if you have now this L is linear, so notice that just the theorem on linearization tells you the following. So suppose G is an algebraic group. So this is a rather general theorem. So algebraic group acting on X on algebraic variety. So I think that you need normality here. X is normal. So that you may think of the following. So L is a line bundle on X. So line bundle on X. On X. Then you can do either the the question is when this line bundle is linearizable. So then just there exists some n such that the power nth power is linearizable. And also there is another option which is and it is up to the taste of the person who is making the research. So you can just pass to the finite covering. So there exists a finite covering, a finite covering. So meaning that this is just a homomorphism of the algebraic group. So homomorphism of algebraic groups, which is finite and such that of course, if you have X, you have a natural action of G tilde by mapping of G tilde on X, by mapping of G tilde to G. So you may think that it does nothing, but it does. So it helps the line bundle to be linearized. So such that L is linearizable. So G tilde linearizable. So you cannot extend the action of G on L, but you can extend the action of the covering of G to L.
What do we mean by being covering? What do we mean?
Finite fibers. Yes, so finite homomorphism. Yes. Of algebraic group. Yeah. So there are two options. Either you can just raise the line bundle to the power, or you can change the group. Of course, from the viewpoint of the action, it does nothing. But from the viewpoint of line bundle, you have some difference. So the next step is to understand. Yeah. So for example, you have the situation, you have conditions. So this is precisely just when you can speak about embedding of X into the projective space. So just L is called very ample. Very ample. So if you can construct, so if you can this map. So if the map, if the map you are constructing via to the projectivization to the set of sections. Is embedding. Yeah, so is embedding. And actually, when you are thinking about this construction, yeah, so this the pullback map. Yeah, so this is if you are using all just so. You have here you have the canonical section of one here, and you have the pullback map of one, and this is precisely the line bundle Yeah, so this gives you the line bundle. Yeah, so you can obtain your line bundle as the pullback of P of E, and this is somehow the best situation that is possible. Otherwise, I mean, as you have noticed, you can take not the whole set of this. You can still take of 1, take restriction of x to of 1, but it can happen that just in general, if you do not require this condition, that it can happen that you have embedding of x to P of V, but so you have this is somehow warning. So it can happen that you have embedding of x into P of V. So here you have the line bundle of 1, and you can restrict you can take the pullback of 1, or you may think of it as the restriction of line bundle to x. Yeah, so this is a restriction of line bundle. But it can happen that, so if you consider the sections of this, so of course, if you take coordinates here, yes, so this set V sits in the sections, so you can take any section and you can restrict into x. So it can happen two things, yes, so that first of all, notice that two different sections of P of V can give you the same sections just if you restrict to x. Yeah. So V maps to, of course, to the set of the sections of this line, the restriction of the line bundle to x, because if you have the section of on P of V, you can restrict it as the section of the line bundle, and but also it can happen that this space is so it can happen that this space is not injective, yeah, because different sections can have the same restrictions a priori, as two regular functions can have the same restrictions to the objects. But also it can happen that here this map is not surjective. Yeah? So here it can happen that there are more sections. And this ideal situation when we're speaking about very ample, that all the sections of these embeddings are precisely that comes from your line bundle. Yeah? So you cannot, by taking the sections and you restricting to x, you cannot obtain new sections of this line bundle, of the pullback of the line bundle. So just this map is neither injective nor surjective. So notice that this is a slightly different situation than the restrictions of regular functions. About injectivity, it is clear, it was clear, yes, so that if you have two sections, if you have two regular functions on some bigger subset, yes, so if you restrict it to the smaller subset, precisely you have the ideal sheaf that of the subset that restricts to 0. So two functions, of course, can have the same restrictions to the subset, and this should occur. But what is not what is new effect here is that this map, it can happen that this map is not surjective. Yeah? So that you start, so that means that you're restricting the sections to X. It generates, they generate some line bundle, but in the same time, when you're already restricted to X, there are more sections that you expect. So that do not come from this embedding. So the next step was to understand, so given this just line, so given the situation when, for example, X is very ample, so we want to construct the quotient, start constructing the quotient. Будьте здоровы. So this passing to semi-stable points. So the idea of looking at semi-stable point with respect to the line bundle is the same that we see here. Yeah, so that if you take this linear system, linear subsystem, you still have the base locus. And the map, the rational map that we are constructing, it is not defined precisely on this base locus. So this is the following. So there exist, so these are such points of X. So such that, so here there exists a section. There exists some n, big N, and the section, so big, so M and the section. So you take the m's power of the line bundle. So here you have the linear action. So you can pick up invariants. So you can pick up invariants on the power of the line bundle. Notice that, of course, if L is linearizable, clearly any operation on this shifts is linearizable. Yes, so that this map is also linearized. So you can pick up this power. So there exists some section, some invariant section, such that the set of XS, so which is the set of S of X, is not equal to 0. So this section doesn't vanish on X, and the set XS. So this is the points Z inside X such that S of Z is not equal to 0. It is a fine subset, so a fine set. Of X. So, or just you may say that just this set is a fine subset of X. So notice that if L is so remark, when L is ample, very ample, ample or very ample. Ample means that the power is very ample. So just L M is very ample. Then the condition that XS is affine is automatic. So notice that when you embed X to this to the projectivization of V, Yeah, so in the setting, so the set is just saying, so the set of the zero sections. Yeah, so the set of, so vanishing of some section is just, so you can pick up this set in P of V and intersect it with the image of X. And if you intersect it with the image, it will be the zero set on X. Yes, so this is the zero set. So here you are considering the points in the projective space. So if you intersect it with the image, since you have inclusion, it will be isomorphic to the zero set of the sections on X. Yeah, and this tells you, yeah, so that this is just the complement to the hyperplane section. So X will be, so since this embedding is closed, so this will be the set of hyperplane sections of so the complement to the set of zeros of X is just so this is just a hyperplane. So hyperplane of P of V. And the complement to the hyperplane is a fine variety, and the X, so this X without set of zeros is a closed variety in P of V dual without these hyperplanes. Yeah. So, and this is just a fine space. Yeah, so a fine space. Just a to the power k, where k is dimension of V. So k minus 1, where k is dimension of V. And this, yeah, so, amen. So this gives you, so this tells you that this set is automatically affine. And if you think of this just, so here we're thinking about m's power. So if you're thinking about m's power, there is a natural map, so you can embed x to the projectivization of V. And there is the so-called Veronese map. So just the so if L is very ample, so this inclusion, so the set of the sections on the power is just can be recalculated as the set as a symmetric algebra of case symmetric algebra of the set of sections on L. So you can pick up so composition of X into P of V and the composition with the Veronese embedding. And here the just if so here if you have the composite map to this Veronese embedding, then you have the section of this section becomes, it is linear, just linear section here. So just S yeah, x equal to 0, it is a linear section. So even if you are thinking about the power of the line bundle, so this composition, which is actually just taking the set of sections, just taking case power of the set of sections. So this gives you the linear embedding of X into this projectivization of Sk of V, where the section now plays a role. So here, the section, if the power, so the section of the kth power play a role of the homogeneous polynomial here, but in this space it is tautologically hyperplane, and So then the complement to the zero set will be a fine variety. Okay. So the idea is now to constructing the quotient is just saying that to construct the quotient, so notice that you may pick up the corresponding sections. So Si in some powers, some invariant sections in some powers Ni, but of course you may put them by raising them to the powers. So just least common multiple, yeah, just LCM of Ni's. By picking LCM of Ni's, you can raise the Si's to the M divided by Mi's, and this will this will give you the section of H0 of X of L in the power of least common multiple. And of course, the zero set of the power of the section doesn't do anything for the set of zeros. Yeah, so that just XS is the same for just XS in this power. So just this collection of sections, and just so you can pick another. So even in the definition, we pick up the sections from different powers of the line bundle, since you can cover X this set by the finite collection of these open subsets. You can put them together in the power of some fixed line bundle. Yeah, so you have, and all of them are G-invariant sections. Yeah, so just SIs can be viewed as the sections of the same line bundle. So G-invariant sections of the same line bundle. And this allows you to construct a natural mapping. So notice that Si do not have common zero on this set, precisely by definition. Yes, so by definition on this common set. So Si tilde does not have common zeros. So you can construct the map from X to, so take the linear system spanned by S1, Sk. So this take this vector subspace. It will be the vector subspace in this invariant space, and we can construct this map as before by mapping the point into the values of this collection of sections. So the idea is that just the final idea of this, that this gives you the map of X to the quotient via invariant sections, and if you have so the section vanish on So the points here are distinguished by vanishing of the collection of sections. Yes, so you can specify the point by vanishing of n minus 1 sections, actually, and k minus 1 sections. And so here you have the map. So this map is constant on G orbit. Yes, so clearly, since sections are invariant, so since Si of Gx is just Si of x, so then this map is constant. This map is constant on orbits, and also it is constant on the following. So it is constant on the collection. It is also constant on the fibers. Yes, so that if you take the orbits, the so-called null cone. So the set of orbits gy such that the orbit gy contains gx in its closure. Yeah. So if you have some fixed orbit and you have the orbits that contain it in their closures, then all of this subset will map to the point via this map. So the idea is that you are constructing quotient, and by this precisely by this construction, and also on each subset. So just so the quotient that you are constructing as the image. So just let's call it phi. Well, phi. So if so the image of the set is covered by the natural open charts. So it is covered by subsets. So you have to take this for each section. You can take x si tilde. So the set of zeros, and then here you have to apply categorical quotient. So this categorical quotient, since just if you think of x s, so you have the collection. Now you're picking up fixed si, so you have the quotients when si is not vanishing. So this this division by Sj, so that if Si is not vanishing, you can divide by one section by the other, and this will be regular function on the set. And now you have the map from Si to the set of so this is will be just S1 tilde. So the S I tilde, etc. You omit I index, and so you are picking up S k tilde divided by S I tilde, and you are just applying the values of so to the point you are applying the values of these sections or of these regular functions on this point. Yeah. For this precisely. So this gives you the map from XS to this quotient. So this gives you the map to the quotient. So of course you have to pick up, I mean it is not enough just to take the covering by xi, you also specify that this remaining section generate the algebra of regular functions on this set, but it is just the set of sections generate the set. So here it is not needed. This gives you precisely the map to this kind of thing, and then you use actually the this thing that we have constructed here is just the categorical quotient. So you want to have the following. So you pick up the sufficiently high power of the line bundle. So note that. So we pick up sufficiently high power of the line bundle such that the set XS is also so the set of regular functions is generated by just S divided by Si, where just S runs through the collection of sections of this power of the line bundle, and S is not equal to Si. So this collection of sections induces the generate the algebra of the regular functions on the set, and this allows you to say that and also you want to when you're thinking about this affine variety, you also pick up sufficiently high power such that the invariants, so these invariant sections that we choose now these are invariant sections of M, they generate the algebra. So you pick up the functions on this X, and they generate invariant functions. Yeah? So this can be achieved by taking sufficiently high power of the line bundle. And so when you have generated this algebra, yeah, so this then you are by this quotient. Yeah, so then you are almost done, because this tells you that this map, if you restrict it to particular to particular chart, it will be the embed. So this invariants will just define an inclusion of this set. So because this is just a spectrum. So if you think of this as the quotient of affine variety, this is just a spectrum of this algebra. So this will induce the inclusion of this set in the image of this one as the just taking excess and taking its image. And so this will cover the image of phi by these charts, and each of them is the quotient for its own affine chart. And also, so that they are glued just because, so you can think of them as, so you can look at the corresponding functorial properties and see that they are glued consistently. So that means that if you have two open subsets, so corresponding to XSI and the XSJ, so here there is open subset corresponding of non-vanishing of two functions, so they all map to the following picture. So here you have XSI modulo J, so here you have XSISJ modulo J, and here you have XSJ modulo J. So you have more or less this explains the construction of the quotient. So the idea is that you are making good conditions in order to specify that your thing is covered by invariant open charts, and you're doing it in a clever way, and then you are just taking quotient on each chart separately. And notice that, so here you should, of course, know the following, that so this thing maps to the open subset on the set of invariants. Here, so if you specify the non-vanishing of Sj, it also maps to the open subset here. But this is more or less clear, because this is just saying that, so if you have if you think about defined variety, so if you have some invariant function, then of course, so vanishing of this function gives you the vanishing of, so it is still invariant, so you can think of this function as the function on the quotient. So this maps precisely to the set of zeros of this function, and this is precisely pre-image of this set. So I mean, so the vanishing of f here is precisely the image. So if f is equal to 0 here, it is precisely image. So the image is precisely vanishing of f, thinking of this as a function. So an invariant. So non-vanishing of f is the open subset here. So, and also it is a fine open subset because it is non-vanishing of f. Yes, so the non-vanishing of some function on a fine variety. So this is fine when we have constructed the quotient. And this the complement is also a fine variety. Just since it is non-vanishing of invariant on a fine variety. So maybe it is a good point to stop to make a break here, and after the break I shall explain why this set is accessible and how we should study them by just some technical procedure related with one parameter subgroups. So I shall introduce the stability functions and tell how to calculate them in particular cases and explain this approach of Hilbert-Mann. So let us continue. And so the question is, can you hear? Can you check the sound? Okay. So so the next question is the following: how can we calculate? So how we can check explicitly? Working, yeah. Okay, great. So the question is how we can check in practice. How to check in practice? Check in practice that the X is semi-stable. So here I wish to start with model situation. Yeah, so notice that just from the when you are thinking about the action, so if your X is chosen in a good way, yeah, so you are thinking about the following. So you are thinking about the embedding of X in the projective space. So via this line bundle O1. And here you may think about the fine cone. And when you are thinking about the fine cone, so here you have the orbits just here you have the just what means invariance. So here you have the orbits. Yeah, so of course cone contains, I mean, if you're thinking about the cone contains 0 in its closure. Yeah? So the question is that when you can pick, so homogeneous invariance. So just this meaning that the sections, so for homogeneous invariance, I call the sections of the powers of the line bundle. They define homogeneous polynomials, so they are homogeneous polynomials. Homogeneous polynomials on X tilde. So we are thinking, so where we cannot, so if you look at all homogeneous polynomials for all powers, so so of course for constructing a given embedding, you can pick up a fixed power of m. However, if you want to study semi-stable points, you are picking up all possible powers of the line bundle. So this means that you are looking at all homogeneous invariant polynomials, and the set where, so the bad set, the non-stable set, is equal to this set of just 0 set of all invariant homogeneous polynomials. So this 0 set are precisely, so the bad set means that bad set is equal to the vanishing of all, so vanishing on V of all invariant homogeneous polynomials. But notice that I claim that it is also, so it is equal to the set of orbits that contain 0 in its closure. So this is the set of orbits. If you consider this just of orbits of X of the cone that contains 0 in the closure, and this is more or less equivalent condition, because if some polynomial vanish identically on the orbit, it of course this so this means the following. So if you have orbit and it is not, so if you have orbit on X and the orbit doesn't contain 0 in the closure, then this orbit contains some other orbit in the closure. Yeah, so this is closed orbit. So you are thinking of everything sitting in V tilde. So you have 0 set. If this orbit doesn't contain 0 in the closure, then there is other closed orbit or orbit. So such that Gy is contained in the closure of Gx. And now you have to use the reductivity of the linear reductivity. So there exists invariant. So f it is an invariant function. So it can be viewed as an invariant function on the cone, but it is also can be lifted to invariant function. So if you are using linear reductivity, this can be viewed as a linear function, G-invariant linear function on the whole V. Yeah, so you can lift. So you can lift the element. Of course, I mean not as the subalgebra, but you can lift invariant element from here to here because of the splitting. Because here you have this just splitting, and the G is reductive, and this gives you the invariant polynomial that so this polynomial such that f of so it vanishes on so it vanishes on 0. This is tautologically, but because it is homogeneous. But f of Gy is not equal to 0. So this is what we proved about the separating two closed subsets by invariance. Yeah. So you can always, given two closed subsets, you can find the polynomial which vanishes on one subset and doesn't vanish on the other. So of course, so here you have to just be a little bit. So here you have to be a little bit cautious because you want the polynomial to be homogeneous, but of course it is clear that thinking of it is clear that you can achieve this without, I mean by this is an easy exercise that you can achieve it here by taking not an arbitrary polynomial but homogeneous polynomial. So this notice that this thing consists of homogeneous polynomials. Yeah? So this is a cone. So the ideal is generated by homogeneous polynomials. So you see that you will have this kind of thing, and this will tell you that of course if you have the orbit which doesn't contain 0 in the closure, then you you will have the polynomial that is not vanishing, and this belongs to the semi-stable point subset. If you have the vice versa, it is also so easy, because if your orbit contains 0 in the closure, then the homogeneous polynomial should have the same, invariant homogeneous polynomial should have the same value. So all invariant polynomials will vanish on this on the orbits that contain 0 in the closure. Yeah? So you see that this is more or less equivalent to check these two things. And now I want to discuss how to check this for particular action. So, and here we also will see that the difference, for example, what is how the linearization arises. So suppose X sits inside P of V, and here you have the action of one parameter subgroup. So you have just a multiplicative group, GM. So this is given by the element lambda P. Is just GM acts linearly on V. Yeah, so GM acts linearly on V. So if you have GM action, you can diagonalize. Yeah, so diagonalize. So this means that you simply act by, so you simply act by, so you have a basis, E1, En, where the action... А вы можете перейти к другой доске, а то я не могу дверь закрыть, извините. Я тут мучаюсь. Вот. Прогнал бедных. Yeah, so you have the diagonal action, so like T and M1, etc. So on each vector it acts by multiplication by the scalar. But notice that the scalar should be homomorphism. So what is the character? So here you should write the character, but the character is what? It is homomorphism from GM to GM, but homomorphism from GM to GM is mapping T to some power of T. So the action looks like the following. Just you are raising in some powers the coordinates here. So you are just mapping these basic vectors to this corresponding. So you multiply by the powers of T. And also, so you can write this down as, so you can take the order such that mk will be, yeah, so this, so here you can think also by coordinates. Yeah, so you're just multiplying coordinates by these numbers, so each EI maps to PMI EI. Yeah? So you may just think that the numbers are ordered. Yeah? And here you will have the following situation that the first, so here the first collection of numbers up to K1 will be, you will have the same numbers, then you will have some equality, and then you will have some K2. So the collection of equal numbers here and here. So then the idea is the following. So if you have, suppose you are taking the vector with non-vanishing components. Yes, so you are taking V. So here you are thinking about the support. So you can think about the support of the vector. So here, if you have V written in the basis xi ei, so the support of V. So the collection is equal to collection of non-zero coordinates. Yeah? Of non-zero coordinates. And also you can write down the weights of this non-zero coordinates. So you can associate, so on the line, you can write down, so on Z, you can pick up the weights of N2, etc. And so here you will have not all coordinates that are not zero, so it will be EI1, EI2, EIL. So some collection of integer numbers, possibly there will be zero, possibly not. So you can write down this collection of zero numbers on the line. So now you have to understand if zero has zero belongs to the closure of the orbit. So now the orbit is just the image of this map, and you may ask the following: that so you are taking this vector, and you are taking this one parameter subgroup, and you may ask if zero belongs to the closure of the orbit. But notice that when you are speaking about one parameter orbit, it is not only the orbit of GM. It also has the order. Yes, so just the parameter t. There are two choices. Yes, so for the generator t, you may pick t or t inverse. Yeah, so that's why picking t also gives you the. So in general, you can so GM sits in project. So it sits in the projective line. But here you have two limits. Yes, so the limit to zero and the limit to infinity. Yes, so you have, when you fix parameter t, you have two options to take the limit. T tends to zero and or t tends to infinity. So here in our picture, you can also pick up the orbit and look at the limit t tends to 0. And if t tends to 0, so notice that what happens. So you have the collection of coordinates, and some of them just, if you are picking up negative ones, they tend to infinity. Positive mi's tends to 0. Yeah? So you see that this tends to 0 if and only if all mi's are positive. Yeah? In the support. So so you are looking at the support. So you are picking 0. And all powers of non-zero coordinates should be on one side. Yeah? But notice that here, just since you can pick up, so here it, so you can pick up the t tends to infinity of lambda t of v. It is the same as saying that t tends to 0, but you are taking the inverse of the one parameter subgroup 1 over this. So the inverse is just taking lambda of t inverse. Yeah? So the inverse one parameter subgroup is just taking by definition lambda of t inverse. And this so this is equivalent as mi lies on are all negative, yeah, where for mi's lies in the support. Is it clear? Yeah. Yes. Yeah. So Вы как-то подзависли, нет? Что? Понятно? Да, но so the next step is to reformulate this. So what does when you pass to projectivization? So the question, what happens when you pass to projectivization and take the limit t tends to 0 of lambda t of v? So of course you do not have 0 in the projective space. Yeah. So now you will look at, so let us write down the homogeneous coordinates. So of course there will be, so let us enumerate for a given vector the homogeneous coordinates, so which have non-zero entries. Let us put it in the first place. Yeah? So you are picking up, so here you are writing down Tm1, etc. You have the collection of Tm1. And here you have the collection of TMK. Yeah? So the coordinates are multiplied. So here you have the collection of coordinates. And these homogeneous coordinates are multiplied by Tm1. And so some other larger T and the T with this MK. So the question, how to take limit here and what is the limit? I mean, I cannot just take t tending to 0 here because I will get 0 point. So I should do something, the operation which is also the operation I have in projective space, but after I'm doing this operation, I can pass to the limit trivially. So, for example, if if m1 will be 0, yeah, then if one will be 0, then there will be a collection of coordinates. They stay stable, yeah. And there will be the remaining coordinates will have a positive, I mean, since I have enumerated them, just the next coordinates will have positive power. So those that are multiplied by the positive power when t tends to infinity will to 0 will vanish. And you will have only remaining first coordinates. So how we can achieve this? Yeah, so you are having the following. So so here you have x0, etc., xl. Yeah. So and here you have the coordinates. So here you have tm2 minus tm1, xl plus 1, etc. And you have remaining just coordinates xk, where you have tmk minus m1. And here you have 0 coordinates. So the idea is that so the limit is just the first coordinates where they are equal. Yeah. So the limit when t tends to 0 is just the first coordinates when they are equal. And if you are thinking about these coordinates, so this is limit in projective space. But if you are thinking about the just geometric situation, then you have the following. So you just yeah. So and this can be formulated, of course, as follows. So the limit point is the part of the support corresponding to the minimal element. If you are reversing the limit, yes, so you are having, you have to take the elements in the support that are raised to the power which is maximal element. Yeah. So if you want to just take go to infinity, you just change the elements by the negative sign. And geometrically, this means the following. So geometrically means that on x, so there is a fiber And you have a point x on this x, and then you are applying the one parameter subgroup, and the limit of one parameter subgroup is fixed. It is of course fixed point. So this is fixed by a one parameter subgroup. Yeah, so by lambda t. And so this is precisely this point, because you are multiplying by the same value. So the t in the same power. This is clearly fixed because this gives you equivalent element in the projective space. Okay. So the idea is the following. So if you have this limit point, then L was so you have the line bundle L. So the fiber over L is mapped to itself. So the fiber lambda t maps. So the fiber pi inverse of y to itself. And this is multiplication by some number. Yeah. So this will be yeah. So this map, yeah. So lambda t maps the fiber to the fiber, which is over the fixed point. So since y is fixed by lambda, and it is multiplied by, so this is multiplication by some number, and this number is clear. Yeah? So this, if you look at this specific point, so the multiplication is precisely this this element m1. Yeah, so the minimal element. So multiplication by t m1. Because we have checked, so the proof is checking. Proof we have done it. So this is checking in P of E. Because it is not, I mean, we are thinking about this sobriety of P of E. And we have done this calculation explicitly, so the fixed point is x0, xl, and it maps, so this is precisely, so it maps precisely to the point tm1, x0, and tm1xl, and so checking what is this number can be done via taking the section and looking how this section is changed. Yes, so that just if you so checking this number is the same as taking semi-invariant section. So just so taking section Si of, so taking, actually you can take arbitrary section and look at, I mean, if you know that the fiber is mapped to itself by lambda t, so you can take the section, you can take the value of this, and you have to compare the value of the section and the value of the section where you apply lambda t. Yeah, so this is fixed point, but on the set when you're applying section, this will be different one. So this is precisely the number that multiply the fiber by this one. And it is very easy to do when this section is semi-invariant. So you can pick up. And of course, the only condition should be that this is non-zero section. Yes, so this section is non-zero. So you can pick up precisely one of the sections. So pick just s equal to x0, and x0 is changed by tm1 x0. So precisely the value, so the corresponding multiplication by m1. So you can reproduce this number. I mean, you can say what is that. You can reformulate this proposition as follows. So that just that lambda t contains so the orbit of the corresponding vector contains 0 in its closure. Yeah, so this is equivalent. V is unstable. Is lambda t unstable? So this is reformulated that lambda t of E contains 0 in its closure. And this can be reformulated as follows. So the just the support. So just ni's the mi's the just so you're putting the weights on the support. So you're picking the weights for the support. So you're taking the support of the vector and picking up the weights. The weights of the coordinates mi, and just mi should be all so all of this mi's should be positive. Yeah, so so the minimal one. So you can reformulate either that all of them are positive, all mi's are positive, or minimal one. M1 is positive. Yeah. So if it is positive, then lambda t contains 0 in the closure. And you can, this is a reformulation in terms of vector space, the action on the vector space. And this can be reformulated in terms of projective, in the projective setting. So the limit of the point lambda t of x. So so you take the limit point of this one parameter subgroup and take the weight so of preimage of the map lambda t that maps p minus 1 to p minus 1. So this is precisely multiplication by t to the power m1. Okay? So is it clear? Yeah, so this correspondence. So the idea is to each point and one parameter subgroup, you and the line bundle. So you pick up the line bundle. You are picking up a linearized line bundle. You pick up one parameter subgroup, and you are picking up so the point. So this is precisely M1. Yes. So this is just you are calling that this is a number M1. So if this number is positive, then 0 is contained in this closure, and if this number is negative, it is not contained, because just the numbers will be like this. Just it will tend to infinity. But of course, the general situation that lambda t, I mean not this one, I mean this limit. Yes, sorry. So the limit when t tends to 0. But now, of course, when you're thinking about instability, so you have to say just what does it mean that So x is unstable with unstable with respect to lambda t. If you are taking the not the limit but taking the closure of V, and it contains 0. And here you have two options. Yes, so you are taking just the infinity, and so you are taking when t tends to infinity and the t tends to 0. And this happens when m1 is positive, but it is unstable if m1 is positive, and m infinity just mk is also positive, or it can happen if it can happen if m1 is positive. Yes, so that means that just if you tend to 0, all weights are on the right hand side. But in the same time, you can tend to here it is t tends to 0 and v tends to 0 if the weights, if and only if the weights are on the right hand side. But if all the weights are concentrated on the left side of 0, yes, so if you take t tends to infinity, then it will be just when you pass to infinity, this will tend to 0. So this happens if either m1 is bigger than 0 or mk is smaller than 0. And this corresponds to saying that this one parameter subgroup, so this means that a point is, and the point is stable if you cannot say this. So if the point doesn't contain 0 in its closure, so lambda t. So it is one finds out that it is easier to say that that something doesn't contain 0 in the closure. That means that 0 sits between m1 and mk, so between the largest and the smallest value. And this means the following, so that so thinking of m1 and not be able to have a limit. So if you have taken a minimal value and you are thinking about m1, so thinking that you cannot take a limit with respect to t tends to 0, meaning that m1 is negative. So the stability means that just mu of lambda t x is negative, and it is also negative for, so x is lambda t stable. So this is reformulated as both functions for lambda and for lambda inverse is also negative. Yeah? So non-positive. So this means that you can formulate the stability in terms of this function. So this function takes only negative values. So the idea is now to apply this to in general setting. So, and this is precisely Hilbert-Mumford criterion. So let me formulate this separately. So maybe, so you are remembering this, that you have this stability function, and saying that the point is stable, meaning, so you can say it in the geometric terms, meaning that support, the point is unstable if the support doesn't contain 0. The support can be viewed as the convex hull of this set of points. Yeah, so the convex hull of the weights doesn't contain 0, or it is in the view, just if you think of this as numerical function, the value of numerical function is always negative. Yeah, so because so this is, I mean, if 0 is contained in between these two things, if you apply t equal to 0, then m1 has negative value. If you apply it to t inverse, you have to take minus mk, and it will have also negative value. So, so the idea is to say just why tori are so important and why one parameter subgroups are so important, that you can reformulate this thing in terms of one parameter subgroups. So Hilbert-Mumford criterion. So this criterion is checking that the orbit is closed. Yeah, so if Gx is closed and Gy contains x in the closure, then I claim, so then what does it mean? Yeah, so this from the viewpoint of just algebraic geometry. So this really means the following. So if one variety is contained in the closure of the other, there is a curve that has, so in one variety, that has a limit point in the other variety. Yeah, so that means that there exists C, such that C without 0 lives in G of y, and the 0, so C without some point, and the closure, so the point precisely lives in the closure, in this closed orbit. So if you have something in the closure, you can pick up the curve that is passing through this Gy and tending to this closed subset. So the Hilbert-Mumford criterion tells us that this can be reformulated in terms of one parameter subgroups. So then there exists lambda t, one parameter subgroup of G. Such that lambda t, and some point, so such that the limit of lambda t y, where t tends to 0, is equal to x. Okay? So notice that everything, can, if you wish, can be checked. The point y can be just moved by g, and the point x can be yeah. So this means that better to say that it sits in gx. Yeah. So that the limit point. So instead of taking arbitrary curve that tends to some point on the closed orbit, you can pick up one parameter subgroup of g. Yeah. So that lambda t maps gm to g, such that you can pick up this one parameter subgroup, and this just has the limit here. So the idea is just so if you have this theorem, then this tells you that our stability condition can be reformulated. Yeah, so it can be reformulated as follows. So
this one parameter group is usually not unique.
yeah, it can happen that it is not unique. Yeah. Well, I mean, yes, and it is usually not unique. So you can you can think of and actually it is not. Yeah, but there is a theory that allows you to take be it unique. So if you are claiming that the function, so that this one parameter subgroup has tends to this orbit in the fastest way that it is possible, then it is unique. So I shall draw the picture in a second. So this is, yeah, so just before, it is not unique. So, so the idea is that checking stability reduces to the following. So here, of course, we are having specific orbit, which is zero orbit. So stability, so to check, so claim. And this is precisely Hilbert-Mumford criterion. So checking stability is checking that just equivalent of checking that zero is not in the closure of the orbit where you're thinking of it as a cone embedded. So I'm thinking of x as the point on the cone sitting inside the vector space. So you're taking the point in x and you are picking up its, so you're having the corresponding affine cone over x. So you have a point x here and you have some lift of this point on V. So, and the V without zero. So if you adjust it, maps to the projectivization of V. Yeah? So, so checking stability of x is equivalent to check that zero is not in the closure of the orbit. And this is, as we have by this criterion, criterion, it is equivalent that there exists one parameter subgroup such that, yeah, so this means that for any one parameter, I mean, so to check that the orbit in the closure is that means that you can find the one parameter subgroup that tend to, if you apply it to your point, then it tends to some closed orbit. Yeah. So of course, meaning that stability, the converse to the statement, it means that for any one parameter subgroup, there is the limit is not equal to zero. Yeah. So notice that I'm writing, I can write down the limit only to 0 because if I want to have two limits, I can take lambda t tends to 0, and for infinity I can take the inverse of lambda, and this will be just contained in this condition if I say that I'm taking all one parameter subgroup, because taking changing parameter t to t inverse is passing to different one parameter subgroup. So this limit of x tilde doesn't contain 0. is not 0. So this is equivalent of checking this. And saying this is equivalent to say that numerical functions, so for for any lambda t numerical function, mu of L related with all one parameter subgroups. It is, and when you apply it to X, it is negative. Yeah, so it is always negative. So non-positive. So this is a criterion written in these terms. And also this notice that if you think about tori, so torus sections, then it is this criterion is most accessible for in the case of tori. So let me formulate it in the case of tori. So criterion for tori when t g is equal to t, and this is obtained as follows. So you have to check. Notice that this. So you are able to. You should be able to write down these numerical functions for the tori. So this means that, so you are thinking, just the action of t on v can be diagonalized. And meaning that for, if you take t it will be written the same way. So but I just writing the characters, yeah. So I'm multiplying the homogeneous coordinates by the characters. And here, if you want to, so of course t from the viewpoint. So if you are thinking about t as gm in some power k, so the t is written, the element of torus is so this is a collection of coordinates t1, tk, and one parameter subgroup is just the map from gm to gmk. So it is just the values of so this t maps to t1, so t and 1, t and 2, etc., t and k. And here, if you are thinking, and the character itself is also the corresponding monomial. Yes, so this is monomial. So each character chi I can be written as the collection of. So you are evaluating it on the torus. So it is t1, tk. It maps to some numbers. So it is mapped to t1. So let me write it down, m1, and for torus you are taking m1 times etc. tk nk. So you are just taking the corresponding coordinates, raise them to some powers, and you multiply. So this is how you are writing down characters. And if you want to have the composition of so you have a pairing between the characters and one parameter subgroup. So this is just substituting the character to substituting one parameter subgroup to the character. Yeah? And this is just saying that you are writing down character of lambda of t. And if I substitute such function in this one, so this values in this function, this is just a sum of, this is just t in the power mi and I. Yeah? So this is written, so this can be viewed, if you think of lambda t as the set of integers and the character as the set of this integer, so this is just pairing. So this can be called a pairing of lambda and chi. Yeah? So the pairing between this collection of integer number and this collection of integer number, just a natural scalar product. So the idea is that if you to do it in practice, the value mi that we calculated are just written. So so this collection of characters can be viewed as a polytope. Yeah. So chi1, chi2, chi3, and chi-l. And the values of the one parameter subgroup can be viewed as the linear function. The linear function is defined by the hyperplane. So this lambda defines the hyperplane on the set of characters, on the set of characters. And if you want to obtain the numbers that we have calculated before, it is just substituting character, this one parameter subgroup to the character. So the numbers that we have calculated, so just the numbers m1, mk that we have calculated are obtained as follows. You have to take the characters and to take the pairing. So to take chi-i and pair it with lambda, one parameter subgroup. So meaning that 0 belong to, so for any, saying that for any lambda, just to say that point is unstable. Point is unstable. If there exists some lambda such that the values are all positive, yeah? So strictly positive means that for the hyperplane means that all points lie on one side of the hyperplane, means that the polytope, so that there exists a hyperplane such that the convex hull of the weights lie on one, so this is convex hull of the weights, lie on one side of the polytope. So lie on one side of the lie on one side of the hyperplane of the hyperplane. And so you asked about the uniqueness of this fastest one parameter subgroup. And the uniqueness also can be viewed here. There is, I mean, if you are looking at the polytope, there is a specific direction. I mean, there is a closed, I mean, if you are thinking about orthogonal plane, there is a, you may think about the closest point to your polytope. And the closest point, closest vector that comes from 0 to your polytope. And if you are looking at the face where this vector touches the interior point, it should be orthogonal to this face. I mean, for example, just I'm writing down the edge, but it can happen that just you have the vertex which is more close than the point of the face. So you are looking at the face where your point is in the interior, and the claim that this distance, this interval is the closest point to the polytope is equivalent that this vector is orthogonal to the interior of this face. So this gives you precisely the direction, the orthogonal direction to this vector is precisely the corresponding hyperplane. So in the sense your question does make sense, there will be a one parameter subgroup which will be the closest. And so this is instability, and stability is the converse to the statement that polytope lies on one side of the hyperplane, meaning that 0 lies in the convex hull of the polytope. So the x is stable, just a point is stable. A point is stable if it lies, if 0 lies in the convex hull of the weights corresponding to non-zero elements in the support. So corresponding to non-zero coordinates of x. I mean, the support is this convex hull of the weights, the collection of the weights. So the support of the vector is the collection of chi I, such that the coordinate, the corresponding coordinate xi is non-zero. Yeah. So just these coordinates play a role when you are passing to the limit. So of course, just in the vector, so if if you have the polytope which is unstable, if you take vectors, so this means that you are taking, so this picking up this weights means that you can find the coordinates with this weights where this coordinates is non-zero and the other coordinates are 0. So if you are putting, so here you can just say that some coordinates become 0. So this means that the support can become smaller like this. Yeah? So if some coordinates start vanishing. So this means that if the point is unstable for a generic choice of coordinates, it is also unstable when you just specialize them to 0. So this means, and it is not too surprising because we already, by definition, we saw that the set of unstable points is closed. But if, of course, you think of, it can happen that if you are thinking about, so you are having the following picture that you are taking the polytope and you are passing to, you are saying that the coordinates corresponding to these two, you are putting them to be 0. So then the support is this triangle. So the whole polytope contains 0 inside it, but some points that are in the closure that we're saying that these coordinates tend to 0. So this points become unstable when you pass to the closure. It can happen that the points become unstable. So this is the most accessible criterion. And if you want to speak about just moduli problems, then usually you are reformulating them as follows, so that you are just taking your object, you embed it in some projective space, possibly by just of sufficiently high dimension, or you reformulate your problem in terms of the points in some high dimensional projective space. If the equivalence relation on your object should be some linear relations, so this means that the objects are equivalent if if some linear they are in the same orbit of some algebraic group, and then you are reformulating, you are picking up some condition which is stability condition, and stability condition, when you are speaking about stability conditions, this is specifying this line bundle, more or less specifying this line bundle. So for different choice of line bundles, you can get different stable points and different results. And this gives you different answers, different modular problems, but some line bundles can be preferable. So maybe the last part, so I want to give some short example, which is rather easy, and you will see how the stability condition arises. So this is the following. So this is just binary forms. So this is called the binary forms. And so you have a SL2 action on, you have natural SL2 action on the set of on C2, of course, and this so you have the natural action on homogeneous SL2 actions on homogeneous polynomials of degree k, yeah? So of degree d. So notice that what is picking a basis? So picking a basis is the equivalent of picking just saying that in this basis some matrices are diagonalizable. So picking xy is specializing, so choosing maximal torus. So choosing is equivalent to choosing maximal torus. So that acts by x by t and y by t inverse. And when the point is unstable, yes, so that so you want to write down but you know that if you have a homogeneous polynomial and two variables, so it is actually written in terms of it is homogeneous, so it can be by the division of y in the highest power, it can be reduced to the polynomial on one variable, but not homogeneous. So you can write homogeneous polynomial into variables in the following way. So you are writing it as the product of x term, y term, and the remaining terms where alpha I are collection of numbers. So alpha I is not 0. Okay? So otherwise it will be the monomial corresponding by x. And so you have this monomial, and you can think of the corresponding limit point and the weight on. So if you are thinking about the projectivization, you can think of projectivization of this space, so of these monomials. So you take this polynomial, and in order to apply our numerical function, you have to apply the limit. You have to take the limit point. so t to the power k xk, y to the power l. So, y will be multiplied by t to the power minus l. Yeah. And here remaining polynomials, so x. What? Yeah, y to the power l. And remaining polynomial will be multiplied by the xt. Yeah, so just minus alpha I t inverse y, t minus 1 y. So of course, yeah. So this, if you want to have the limit, you can multiply and divide. Yeah, so you can write down here t square and divide it by remaining terms, t to some power, and this power can be recalculated. This is just so I have multiplied the bracket by each bracket by t. Yeah, so, and the number of these brackets is precisely d minus k minus l. Yeah. So you have to compare. Yeah, so you have to compare two numbers. Yeah, so you have to see. So what is the number of the limit point? Yeah, so this will tend to y. So at least the limit point will be x to the power k, y to the power l, and y to the remaining power. Yeah, so d minus k minus l. And so you see, yeah, so this will be the limit point, and this will be equal to xk y d minus k. Yeah. So if you want to compare, so the numerical function is the weight on so the value of action of one parameter subgroup on this function. So applying mu of this limit, just mu of so numerical function of this polynomial p of xy is equal to a numerical function. So you have to act by t on the limit monomial. So weight of t on limit monomial so which is precisely this one. Yeah, so xk y d minus k. But this weight is what? It is, I mean, it is tk times t minus 1 in the power d minus k. So this weight, in order to the point to be unstable, this weight should be positive. Yeah, so p of xy is unstable if this weight is positive. So meaning that k minus d minus k is positive. So meaning that d is so k is larger than d divided by 2. So what does it mean? So this means that if you have the monomial, yeah. Yeah, so how this can be reinterpreted? I mean that so the point is unstable if there exists a basis such that k is bigger than d divided by 2. So and this can be formulated coordinate free. So the point is unstable. So just polynomial is unstable. So picking coordinate means so picking s is nothing as picking the basis. But saying that so our condition that if there exists the L of xy, the linear polynomial, such that the polynomial is written as L of xy in some power k, and you have the remaining polynomial x tilde, and this k is bigger than d divided by square. So the claim is that if your polynomial is divisible, so has a root of multiplicity larger than the half of the degree, then the polynomial is unstable. If the polynomial doesn't have such root, then the polynomial is stable. So which is quite convenient. So you see that in practice it is quite easy to do, but of course each time it is, I mean in this example it is easy. In some examples it could be straightforward but more complicated. But of course when your problem becomes more and more involved, it becomes harder and harder to express these numerical conditions in geometric conditions, and it is most interesting thing. Yeah. So the most interesting thing, for example, if you are looking at the space of some surfaces with particular properties, for example, it is the best situation when smooth surfaces correspond, or smooth curve corresponds to stable points, and then but then still stable instability condition is some condition on the singularities, for example, of the curves, or singularities of the surface, of the singularities of the objects you are considering. So the best ideal situation is to reformulate this stability condition in some geometric terms. For example, here the multiplicity of the polynomial is geometric condition. So it is the divisibility by a sufficiently high degree of the linear form is geometric condition. Okay, so maybe it is a good point to stop. And so this is more or less. Oh, thank you for attending my course. It was a pleasure to have you as the listeners.